Hi, my name is dr. Ahmath. In this video lecture, we are going to talk about the chain rule on taking the derivatives. So we are going to try to understand the chain rule intuitively, and we're going to try to do a couple of examples on that. So first of all, I would like to try to understand what is actually the derivative. So let's say you're given some curve, which is simply y is equal to the x. So it is really important for us to understand what is this. So let's say when x is equal to the 1, y is also equal to the 1. So this point is going to have the coordinates 1 and 1. And when x is equal to the 2, then y is also equal to the 2. Then this point is going to have the coordinates 2 and 2. So now the question is, if I change the x from 1 to the 2, from 1 to the 2, how much the y is changing, how much the height of this function is changing. So that's the question. So if we change the value of the x, how much, so x from 1 to 2, how much the value of the y is changing. And that's actually the rate of change of the y. So it's not like how much it is changing. It is basically how fast it is changing when we change the values of the x. So if we don't change the values of the x, so we don't care. So it's like the derivative of the y is the change of the y divided to the change of the x. So this is what we need to understand. And again, so if we are given another curve which is equal, let's say for example, y is equal to the 2x. So this curve is going to be y is equal to the 2x. And again, I would like to understand how much this curve is changing if I change the x. So I'm going to choose one point. When x is equal to the 1, it's going to be equal to the 2 already. So this point is here. So when x is equal to the 1, it's going to be equal to the 2. And when x is equal to the 2, it's going to be equal to the 4. So when x is equal to the 2, the y is equal to the 4. So you see, so, and again, the question is how much the y is changing if we change the x from 1 to the 2. So let's change x from 1 to the 2 and then understand what is the change on y. And again, we can see that the y is changing from 2 to the 4. So the rate of change of this curve with respect to the change on the x is equal to the 2. So that's we call as the derivative of the functions. So the derivative of the function is how much the curve has changed if we change the x, for example. So if you are given, for example, the horizontal line, which is going to have the equation, let's say y is equal to the 1 in this case. So what does it mean? It means that no matter how we change the values of the x along this curve, all of the values of the y are going to be the same. So for example, if I choose this point here with the coordinates, so on the x1, so the coordinates of this point is going to be equal to the 1 and 1 because here is the 1. And if I choose the x to be equal to the 2, this is still going to be 1 on the y coordinates of this point. If I choose the x to be equal to the 3, it is going to be still the y coordinate to be equal to the 1. So no matter which point we choose along this curve, the coordinates are going to be, the y coordinates are always going to be equal to the 1. So it doesn't change as we change the x. So maybe, so it might represent something which is going to change if I change the z or time or something else. But when we are changing the x, it is not changing, right? So the delta y with respect to the delta x is simply equal to the 0. So that's why the derivative of this y with respect to the x is equal to the 0. So you see, so our point in our in this video lecture is this variable of the differentiation. So, well, the derivative of the functions depend on the functions itself, but at the same time, it depends on the variable of the differentiation. So what we are changing in order to understand the change of the curve. So let's consider a couple of examples now. So let's say if you would like to take the derivative of the x with respect to the x, then you're going to use the formula for the power derivatives of the power functions, which is simply going to be equal to the 1. Or for example, if you would like to take the derivative of the y with respect to the y, it's still going to be equal to the 1. So what I want to say here by these two examples is that, so you need to look to this x or y inside your functions or to the variables of the differentiation. So we call this the variable of differentiation as the symbols. So they are simply symbols. So please don't put anything extra on the top of the meaning of this letters. So they are the symbols. So the only thing which matters for you is that this symbol here is similar to this symbol here. For example, if they are the same, then the derivative is going to be equal to 1. For example, the symbol inside is going to be x squared. And if I would like to take the derivative of this x squared with respect to the x squared, it's still going to be equal to the 1 because I'm going to look to these two letters or two functions as the symbol. So this is going to be one symbol. And if I take the derivative of a symbol with respect to the same symbol, it's obviously going to be equal to 1. I could have anything instead of those symbols. For example, I could have even a banana. So the derivative of a banana with respect to the banana is equal to the 1. And I could have an apple instead of banana. Derivative of an apple with respect to an apple is again to be equal to the 1. And again, I just would like to note that there should be correspondence between the symbols inside your function and the symbols and the variables of the differentiation. So if they are the same, you can work with them. But what happens is that, for example, you're given x and a square, and you're going to take the derivative of this function with respect to x. So in this case, then you need to use the derivative of some called standard functions. For example, something in a square or something in a cube or something in the power of n is going to be the power function, and we know that its derivative is equal to the 2x. So this something might be x or might be even an apple. So an apple in the square, and when we take the derivative of an apple in the square with respect to an apple, this is going to be equal to the 2 times the apple. So it doesn't really matter what is this symbol here. Is it whether it is x or whether it is y, whether this is an apple or a banana. So the most important thing is I'm taking the derivative of something in the square with respect to the same thing. So what is difficult now is that sometimes we need to find the derivative of a function which is certainly depend on this x, but not explicitly. So we don't see this at the first glance. So for example, if you would like to figure out the derivative of a juice with respect to the banana, so where I say that, hey, this juice contains a banana, contains a banana, then how to take the derivative of this kind of functions? And that's a question. And the chain rule, it appears, is going to help us to solve this kind of questions. So let's see mathematically what does it mean. So let's say you are given the function, the sine of x in the square, and you have to take the derivative of this function with respect to the x. So the thing is, like, if you are given sine of x, and its derivative is going to be equal to simply cosine of x. At the same time, if you are given x in the square, and its derivative with respect to the x is going to be equal to the 2x. They are the standard functions, and we know how to take their derivatives. But now, if you are given the composition of these two functions, so this is called the composite function, when you are basically plug in x in the square instead of x, then how to take the derivative of this kind of function. So you see, so whenever you take the derivative here, so this variable of the sine was the same as the variable of the differentiation. And whenever we take the derivative here on the top, so the variable of your power function was the same as the variable of the differentiation. Well, here in this function, which we are given, the variable here of your sine is different from the variable of the differentiation. So the key idea of taking the derivative of this kind of functions would be to make the correspondence between these two variables, the variable of your function and the variable of the differentiation. So let's see how to take the derivative here. So the idea would be like this. So if this symbol, x in the square, and this symbol here would be the same, then I could take the derivative, right? So it would be the sine of x in the square, its derivative with respect to the x square. It's clear what is this, right? So I'm going to look to this x square as the symbol, not just the function. So this is sine of something. So I'm taking the derivative of sine of something with respect to the something. What is this? It is going to be simply cosine of the same thing. So as we would do for the sine of x, so sine of x, its derivative with respect to the x is equal to the cosine of x. So that's why sine of something, its derivative with respect to the same thing is going to be equal to the cosine of something. So now you see, so I'm changing this variable x with something different, x in the square. So that's why I have to pay some cost for this. So for changing this variable, and the cost as it appears is just a multiplication of this derivative to the derivative of this new variable x in the square with respect to our original variable. And we know what is this. So this is going to be equal to simply 2 x. So this is how it works. So if I would like to take the derivative of the function, what I have to do is I need to change the variable. So I need to change this from x to the x square because I've got here the x square. Then additionally, we have to multiply this to the derivative of the x in the square with respect to the x. So because we've changed this from the x to the x square, and we have to pay for this a little bit. So, and in general, if you're given the composition of the two functions, so essentially f of g of x, then how to take the derivative of this? So if you would just given f of x, then you could find the derivative of that function, right? So now let's assume that you are given f of something, and you would like to take the derivative of this thing with respect to the same thing, right? In that case, you could take the derivative. So it's going to be, so you need to look to this function as like f of something. Okay, so let's do this. So it's going to be the derivative of f of something with respect to the something. Okay, so you see, so this thing and this thing are going to be the same. But I've changed the variable of the differentiation from x to the g of x. So that's why we have to multiply this to the derivative of the g of x with respect to the x. And that's what we call as the chain rule. So in general, I'm going to write down the formula like this. So sorry that the part of the formula is not visible. So this part is simply g of x, its derivative with respect to x. And again, the idea is like this. So you're going to look to this something inside the f as some symbol, and you're going to just make the correspondence between the variables. So if you're given function of something, and if you're taking the derivative of this function with respect to the same thing, it is possible to take the derivative. So you can just look to this as the f of x, its derivative with respect to the x. Okay, which is doable. So let's do a couple of examples on how to take the derivative using this chain rule. So let's say our first example is going to be this function, sine of e in the power of x. And again, so if you were given as the sine of x, you would probably can take the derivative of that function. So now you need to look to here to this function as the sine of something. So how we can take the derivative of this thing. So if the variable here would be the same as the variable of the sine, so in this case e to the power of x, then we could do that, right? So this is going to be the sine of e to the power of x. Its derivative with respect to the e to the power of x. Okay, so I've changed this because I know what is the derivative of the sine of something with respect to the same thing, because we know that the sine of x with respect to the x is going to be equal to the cosine of x. And again, you need to look to this variable here as the symbol. So this might be anything there. So even a banana. So the sine of banana with respect to the banana is going to be equal to the cosine of banana. So again, it's like a sine of e of x with respect to the e of x is going to be equal to the cosine of x. But since I've changed the variable of the differentiation from x to the e in the power of x, we have to multiply this to the derivative of the e in the power of x to the with respect to the x. Okay, so now let's calculate the things. So it's going to be cosine of e in the power of x times the e in the power of x. So that's going to be the derivative of this function. So let's do a couple of more examples. So let's say you are given e in the power of sine of x now. And again, so we need to look to here as the e in the power of something. So e in the power of x, its derivative is going to be equal to the e in the power of x. And again, you need to look to this x as something. So e in the power of something, so its derivative with respect to the same thing is going to be equal to this e in the power of something. So in order to do that, we have to change the variable of the differentiation. It's going to be e in the power of sine of x, its derivative with respect to the sine of x. So you see, so I'm making the power of the sine and the variable of the differentiation as the same thing, so the same symbol. So you need to look to this as the symbols, not the functions anymore. So I have to multiply this additionally to the derivative of the sine of x with respect to the x. So the sine of x is coming from this one. So this is a new variable which I've changed, right? So which I've introduced. So it's going to be e in the power of sine of x times the cosine of x. So because the derivative of the sine with respect to the x is going to be equal to the simply cosine of x. So let's do one more example. So this is going to be a little bit different than sine and cosine. So the variable of the differentiation is going to be p now. And again, so if you would have, so 1 over p, its derivative is going to be equal to, so we need to use so-called derivative of the power function. So it's going to be p in the power of minus 1, its derivative with respect to the p, right? So if you remember, this power falls down, it's going to be minus 1, p in the power of minus t. It's going to be minus 1 divided to the p in the square. Okay, so the problem is, so we are given not p, but p in the square plus 1. We need to look to this p squared plus 1 as the symbol again. So what we are going to do is I'm going to rewrite this. So the p in the square plus 1, its derivative with respect to the what? So with respect to the p in the square plus 1. So in this case, I would get this like there's something here, and I'm taking the derivative of this thing with respect to the same variable. Very much similar to this function, which we did here. Okay, and again, so you need to learn how to look at the functions symbolically rather than putting some meaning on the top of that. So then I have to multiply this to the p in the square plus 1 and its derivative with respect to the p. So and again, so the derivative of the first part is going to be minus 1 divided to the p in the square plus 1 in the square, right? Because do you remember? So this is going to be the same symbol in the square, the same symbol in the square. So the times is the derivative of the p in the square plus 1. So the derivative of the p in the square is going to be 2p, and the derivative of the 1 is going to be simply equal to 0. So that is what is the derivative of the 1 over p in the square plus 1. And we could do that using the chain rule by changing the variables of the differentiation. So this is what we've learned today. We've learned about the chain rule. Again, so in order to take the derivative of a composition of the two functions, we first of all need to change the variable of the differentiation from the x to this function, which is inside our first function. So here, and additionally, we have to multiply this. So don't look to this part. Additionally, we have to multiply this to the derivative of this new variable with respect to x. So please keep in mind that so you need to look to the variables as the symbols. For example, if you would like to take the derivative of something like an apple in the square with respect to the apple, to the apple, it's going to be simply equal to the 2 times the apple. So that's what is called the chain rule. So I hope that this video was helpful for you. Thank you very much.